Hello everyone, my name is Nitik Kumar Mistry and I am here to present an idea about researchers simplify parallel programming. So, first of all, what is the parallel programming? Parallel computing, parallel programming, or it can say parallel computing, is a type of computation in which many calculations are carried out simultaneously. Parallel computing has become increasingly important as the chip maker that is like Intel or AMD. They are putting more and more processor in just an individual chips. Computer scientists and researchers now believes that the parallel computation are not difficult as previously we have thought. So here is the idea of the parallel computing shown in the figure. Uh, it is operating on the principle that the larger problem can often be divided into smaller and which can solve at the time. Here we can see at the in the figure that there is a problem on the left hand side and they are divided into the instructions and they are given to the specific processor which we can see in the picture. Parallelism has been employed for the many of years, mainly in the high performance computing, but interest in it is grows lately due to the physical constraint preventing frequency scaling. So why we need the parallel computing? So power consumption and consequently heat generation by computer has become a concern in recent years. Parallel computing has become dominant paradigm in computer architecture, mainly in the form of multi-core processor. In parallel computing, a computational task is typically broken down in several, often many, very similar subtasks that can be processed independently and whose results are combined afterward upon completion. Researchers simplifies that the two types of algorithm are part of a class of technique used in shared memory system that are non-blocking, meaning concurrent threads in a program are not halted indefinitely by mutual exclusion. Block-free now generally refers to algorithm that guarantees some concurrent or operations will always make progress. That is, that there is a guaranteed progress somewhere in the system, regardless of scheduling. The more rigorous wait-free algorithm go further, guaranteeing every thread makes some progress. Now, wait-free sits better on theoretical grounds. It is designed to handle worst-case conditions that very rarely occur. The researchers found that using a technique called Markov chain lifting, in which they model the average behavior of multiple threads across an entire system over time to simulate the threads' expected sympathetic behaviors. The results showed that the many problems, the two kind of algorithm will perform about the same. Nevertheless, wait-free algorithm will still be right choice for real-time system where processes have hard deadlines. That's what the researchers say. Now, the world is going for the parallel. The parallel computations has become increasingly important in recent years, moving from the realm of scientific supercomputing into corporate database servers, and into the cell phones and personal computers of users. Limit on energy consumption, heat dissipation, and cheap technology are preventing the speed of individual processors from increasing at the rate we have seen over the past decades. To increase overall performance, to increase overall performance, chip makers are putting more and more processor core on a single chip. Yet using those processors efficiently requires the often difficult task of rendering program to run in multiple concurrent threads. In some cases, such as graphics processing, that is relatively easy, as each processor can be allocated its own separate portion of data. However, many programs contain instructions that need to share data, and programmers often lock those during the program execution, so data in memory is protected while it is being worked on. Some difficulties have programmers that facing are they have employed such locks for the many years, but they charge a penalty. The operations inside a single lock, which might be in multiple tens of instructions, they can become a bottleneck to the overall execution of the system. One goal in this shared memory system is to reduce the sequential bottlenecks uh, caused by the locks. The possible solution can be minimized. So this problem can be minimized by use of the fine-grained locking, which locks off fewer instructions at a time. Yet the use of lock-free algorithms open up the possibility of parallelism at the lowest possible level of granularity, at the level individual machine instruction. Programmers may set a lock in one place in a program but release it at some number of other unpredictable places, making it harder to ring and debug the code. While lock-free algorithms solve some problems, but it still have some difficulty in it. They in turn can be tricky to code and debug. Although the move to parallel computing is leading to increased interest in these algorithms, most programmers need not be concerned with this latest analysis of lock-free versus weight-free. So the one possible another idea is the transaction. In recent years, another lock-free control method has attracted considerable attention, that is called transactional memory. It works like a database transactions which are required to maintain the integrity of database accessed by the multiple simultaneous users. In transactional memory, a unit of code that is reads and writes to shared memory is treated as a single atomic transaction, but the memory is not logged against the access by other threads. If conflicting changes to memory are made by different threads at the same time, the transaction is aborted and the changes are reversed. The net result is the parallelism become potential possible at the machine instruction level of granularity. A hardware-based transactional memory was introduced last year in Intel's Haswell's and IBM's PowerAid microprocessors. Transactional memories are also existed at the some software level. For an example, C, C++, C Sharp, and Java compilers. So it is too early to tell how well the transactional enabled chips will work. Some researchers predicted that the transactional programming model that avoids the locks by hybrid of hardware and software transactions. Transactional memory is like that the ball bearings, where the concurrent parts are synchronized, but the language where it is tightly controlled which part of the program can be shared and modified concurrently can go a long way making a parallel system easier to understand and maintain. By going forward, debate and research surrounding the various methods of concurrency control center on the delays that had occurred a problem of execution and the impact of those delays on the system performance. However, uh, other criteria like power consumption, reliability, availability, and maintainability increasingly trump the performance metric. The largest system now at Argonaut has 750,000 processor cores, and one researcher, Sneer, predicts that the arrival of exascale computing in which a single application run in from 100 million to 1 billion threads that will require a new codes that are hybrids of share memory and message passing architectures. And at those levels, system designers may worry less about which program produces the smallest delay than about which ones are easiest to debug, which one consume the least power. The concept of lock-free, wait-free, transactional memory are at present at mostly of interest to programmers writing high-performance parallel system software, such as in operating system or communication software layers. But this will be charged as the number of cores on a chip increases. About this paper is quite really good, but some of the confusion at the starting. This paper is written to the point, but there are some high levels operating system algorithms that will require some more explanation and some more example. But example and inclusion is nicely done, and researchers' ideas and comment and concept are nicely narrated in this uh, paper. The future work about the parallel computation is the economics has changed, technology has changed, and there are all kind of exciting new applications like machine learning and graph search. All these kind of things are carried out for the better parallelism. Thank you.